Very good morning, all of you. And this is Karthik, Assistant Professor, Department of AML, Annamacharya University. Today I am going to do a video lectures on AVL Tree Introduction and Width Rotations with the subject of Advanced Data Structures and Algorithm Analysis. First, let's see what is AVL Tree. Introduction. An AVL tree is a binary search tree, but it is balanced tree. How it is, where it is balanced? An AVL tree is a binary search tree, but it is balanced tree. So here balanced means difference between height and right subtrees must be -1 or 0 or 1, and this is nothing but the balance factor. The balance factor is always -1, 0 or 1. Okay, these are the numbers where we are getting while running the in AVL tree. Every node will one extra information is known as balance factor. First of all, we should know what is balance factor. First, we need to know the balance factor formula. Balance factor equals to height of left subtree minus height of right subtree. And an AVL tree is named after its two inventors, right? GM Adelson Veleski and EM Landis. These are the two inventors are published their AVL tree in the year of 1962, and this is an example of AVL tree. Let's see all the observe the here it is a root node, and all the left side values are greater values of its compare with its root node, and all the right side values of greater values compare with its root node. Okay, and let's see, so these are the also parent node, these are the two children's. Okay, compare with these two also, these nodes also. Left side values are always lesser values and right side values are always greater values, and this is an example of an AVL tree. Oh, and this is so we can find out the balance factor of each and every node by using rotations. Okay, now let's see the rotations. After every insertion or after every deletion, we need to check the balance factor. If it is other than -1 or 0 or 1, then we can perform the rotations. We make the tree is balanced. Okay, in that case, we can insert every node or every deletion. So we need to check the balance factor, and the balance factor is -1, 0 or 1. Okay, we are getting these numbers. At that time the tree is balanced. We are getting not these numbers, at the time the tree is imbalanced. So we need to use the rotations to make the tree is balanced. Okay, and let's see the note. All AVL tree are binary search tree, but all binary search trees need not to be AVL tree. Okay, binary search tree means if you compare with its root node, all the left side values are lesser values and all the right side values are greater values. That is only binary search tree. But comes to AVL tree, same process, same steps you have to follow in also AVL tree. All the left side values are lesser and all the right side values are greater, but we need to check the balance factor. The balance factor is always greater than -1, 0 or 1. Okay, we are getting only these numbers. All binary search trees are binary search tree, but all binary search trees need not to be AVL tree. Okay, right. And then next is see the rotations. Sorry. These are the we have two types of rotations: single rotation and double rotation. Again, single rotation we have to divide it into again two types: left rotation and right rotation. Double rotation also again you have to divide the two types: left right rotation and right left rotation. We can call in the short form LR rotation or RL rotation. Okay, let's see the single left rotation. In left rotation, every node moves one position to left from current position. To understand LL rotation, let us consider the following insertion operation. Okay, let's see this is the diagram. So we need to insert a 1 2 3. Okay, first let insert 1. This is a one node, and we can insert the so sorry, after every insertion we need to check the balance factor, right? First we can insert the 1, then we can calculate the balance factor. Always the balance factor is 0 because we have only one node. And let us insert the second element, 2. Okay, these are greater values, so we need to insert the right position in the middle of 1. So again check the balance factor, -1, 2. So again on the last one we can insert the 3, 2 of 3. So this is a greater value of 2, so we can insert the right position. And this is the, so we can check the balance factors of each and every node. So we are getting the final balance factors of 0, -1, -2. So how we can check the balance factor? So we have a formula like balance factor equals to height of left subtree minus height of right subtree. What is, first of all, before going to calculate the height is nothing but the how many nodes will be connected in that particular node. For example, I want to calculate the balance factor of 1. In this node we have only 2 nodes will be connected, and so the balance factor, so the height is 2. Okay, this is to calculate the height, and based upon that height we can check the balance factor of each and every node. Or if in case the tree is not balanced, we can apply rotations. And single left rotation means one position to left from current position, one position to move from correct position. Each and every node moves one position to from current position. Okay, after applying the LL rotation, here it is the final tree we are getting. Okay, all the nodes must be in the balance factors or 0 0 0. Okay, and this first rotation. And let's see second rotation, single right rotation. Single right rotation, every node moves one position to right from current position. To understand LL rotation, let us consider the following insertion operation in AVL tree. Okay, this is an example. First we can insert the 3. Okay, 3 will be inserted, and again next 2 will be inserted. 2 is a lesser values or 3, so we can insert the left position of 3. Again 1 will be inserted also. 1 also is lesser values of 2, so 1 is will be inserted in left position. Then so we can apply the single right rotation up rotations. So one position to move from right from correct position. So after moving one position of each and every node, and also check the balance factor, we are getting the 3 of balance factor is 2. Okay, these are the numbers are in between in the range of -1 1 0. So this is not a balanced tree, so this is imbalanced tree. To make the tree is balanced, we can apply the rotations, and then after applying the rotations we are getting the balance factor like this. So this is a balanced tree. Let's see one more node, right left rotation. Okay, same throw we can apply 2 rotations on only single diagram. RL rotation is sequence of single right rotation followed by a single left rotation. In RL rotation, at first every node moves one position to right and one position to left from the current position. To understand the RL rotation, let us consider the following insertion operation in AVL tree. Okay, these are a diagram. These are the numbers to insert to generate an AVL tree. First, let us insert 1. Then after 1 will be inserted, check the balance factor. The balance factor is always 0 because they don't have left and right child. So that is the tree of balance factor is 0. And the next one, third will be inserted. Third element will be inserted. Third is the height element. So it's the largest element of 1. So 3 element will be inserted in the right of 1. Right of 1. Again 2 will be inserted. 2 is above 1 greater value and below of 3 lesser value. So we can insert the 2 is 3 of left. After insertion all operations, so we need to check the balance factor. The balance factor is always greater than 0 1 or -1. So After calculating the balance factor, we are getting like this: minus 1 is the balance factor is minus 2, and here it is 1, here it is 0. So we can apply the one position to right and followed by one position to left. So we are getting like this. Same applying, this is completely LL rotation. We can apply again here LL rotation. So the here we have a balance factor of 1 is minus 2, so we can apply until the tree is balanced. After applying all the rotations, so we are getting the final balanced tree. Okay, all the nodes in must be in zeros. This is completely working of RL rotation. And this is LR rotation. LR rotation also same is completely opposite of RL. RL rotation is a sequence of single left rotation followed by a single right rotation. In LR rotation, at first every node moves one position to left and one position to right from the current position. To understand these rotations, let us consider the following insertion operation in AVL tree. These are the numbers to insert: 3, 1, 2. First let us insert 3, and 3 will be 3, 1, 2. First let us insert the 3. Again, after insertion of 3, we need to insert the 1. So 1 is the lesser value of 3. We need to insert the left position of 3. Again 2 will be inserted, and 2 is a one position of right position of 3. So we need to insert the 2 is in right position again. And this is the, we can apply the rotations of LR rotation. After applying LR rotations, we have to generate and balance factors are 2, minus 1, 0. Okay, minus 1, 0 also is okay, but 2 is, the tree is not balanced, that indicates. So again you have to apply LL rotation. Again also we are getting the, in the third element of the balance factor is 2, 1, 0, remaining 2 nodes. Again after applying LL rotation, we need to check the balance factor of each and every node, and we are getting the same balance factors are 0, 0, 0. So this is the balance factor of tree. Okay, now let's see the working of all the rotations in the form. And this is LL rotation. First node will be inserted. Again check the balance factor, always 0. Again one more node will be inserted, B. B is a greater value, so right side will be inserted. Again check the balance factor of B, also 0, because they don't have left and right child. Again check the balance factor of A, because A having one node, one right node. So we know that the formula balance factor equals to height of left subtree minus height of right subtree. So height of left subtree is 0 and height of right subtree is 1. 1 minus 0, we are getting 1. Again one more node will be inserted. Check the balance factor, 0, and B balance factor is 1, A balance factor is 2. So A balance factor is, we are getting the 2 values, so we need to make the tree is balanced with the help of rotations. So we are applying the rotations, how it will generate, let's see all of you. So B will be moved one position to right, and C also one position to left. And again we can calculate the balance factor of each and every node, 0, 0, and 0. This is the tree of LL rotation, working of tree LL rotations. And RR rotation also same. One node will be inserted and another node will be inserted. We need to check the balance factors, 0, 1. Again one more node will be inserted, that is A. Again A balance factor is 0, B balance factor is 1, because B having only one node, and C balance factor is 2. We have the node having 2 nodes or 2 children, so the balance factor is 2. We can apply RR rotation, one motion moved one position to right. So how this is the working of RR rotations. Again check the balance factor of each and every node. After getting the balance factor of 0, 0, 0, this the tree is balanced. Again same LR rotation also. One node will be inserted, another node will be inserted, and C, check the balance factor of C, 1. Again B balance factor is 0. Again A balance factor is 1, C balance factor is 2. C balance factor is 2, we are getting the not value, that is 2. So we make the tree is balanced by applying LR rotation. How LR rotation will be applied? In that A, one portion move to right and B replaced with A. So finally we can apply RR rotation, and after applying RR rotation we are getting the balance factor like this: 0 0 0. Okay, this is the tree is balanced, and this is all our rotation. Same process. A is 0, the balance factor. C is 0, the balance factor, and A is 1. Again one more node will be inserted, that is B. Balance factor is 0. C is balance factor is 1. A balance factor is 2. A balance factor, it is not in the balance factors 1 0 minus 1, so we make the tree is balanced. We can apply RL rotation. One portion to left replaced with B, and A root node will one portion to right, so A replaced with B and B replaced with C. Finally we can check the balance factor of each and every node: 0 0 and 0. Okay, this is our working principle of RR rotations. Thank you.